talking about the heterogeneous nucleation. Okay, and in that context, we discussed about the Kohler's curve, so-called Kohler's curve, which tells you about the growth of the cloud droplets. Okay, uh, versus the supersaturation or the relative humidity of the ambient environment and the rising air parcel. Okay, that's what we had discussed in the previous class. We also discussed about the cloud condensation nuclei, various sizes of the nucleus, CCN, the cloud condensation nuclei, called the Atkin nuclei, the large nuclei and the giant nuclei based upon their sizes. These things we have discussed in the last class. Okay, we also talked about the microstructure of the warm clouds that also we discussed in the last class. Okay, in which we said that the three most important parameters for the cloud microphysics is one, cloud liquid water content. Okay, number two, the cloud optical thickness, the effective radius of the particles. Okay, the cloud droplets concentration. So these are the important cloud microphysical parameters which identify the contents of the clouds and also depending on the types of the cloud, right? And some of these are also very important for the calculation of the radiative fluxes. When we talk about the cloud radiation interaction, then some of these parameters like single scattering, albedo, the symmetry factor, etc., those things we have studied in the radiation chapter. So those things are important also for the cloud microphysical parameters, or we can say that the cloud microphysical parameters which are computed in this way are also used to compute the radiative fluxes. When you compute the radiative fluxes, then some of these parameters are required for the computation of radiation fluxes. Okay, we also talked about the uh, droplet diameter versus the droplet concentration. Okay, in the last class itself, we have talked about that. And also we talked about the vertical velocity inside the cloud. That means inside the cloud, as you know, there are updrafts and downdrafts. Okay, so when the updraft is there, that is when there is a strong rising motion. Okay, the vertical velocity is positive, and when there is a downdraft, there is strong sinking motion, and the vertical velocity is negative. Those things we have discussed, talked about in the last class. This diagram also we have discussed in the last class. Okay, droplet radius versus the droplet concentration for different types of cloud, like for the marine cloud, for the continental cloud. Okay, those things we have talked about in the last class. I'm just reviewing, okay, for your sake, that continuity will be maintained. What you have discussed earlier and what we are going to discuss now. Okay, this is the global distribution of the cloud optical thickness, and then we also talked about the liquid water content. Okay, uh, at height above the cloud base, measured versus the one which is estimated from the SQT log P diagram. We had uh, talked about or learnt about the SQT log P diagram, diagram, etc. in your atmospheric thermodynamics chapter, if you recall. Okay, SQT log P diagram. And from the SQT log P diagram also, as we had discussed earlier, many things we can compute about the cloud. Okay, like what is the cloud temperature? Okay, what is the liquid water content of the cloud? What is the base of where is the base of the cloud? Where is the top of the cloud? All those things we can estimate based upon the diagram or the SQT log P diagram. Those things we have discussed in the atmospheric thermodynamics, isn't it? Do you remember the SQT log P diagram, the diagram, etc.? Hmm? Barsa, Trishna, do you remember those things we have discussed about that? earlier. Am I
Yes, sir,
audible?
in the
Okay. Yeah,
thermodynamics chapter.
exactly. In the atmospheric thermodynamic chapter, we had discussed about the diagram and how the cloud base, the cloud top, the cloud temperature, the mixing ratios within the clouds they are computed, and so also we can compute or estimate rather the cloud liquid water content. Okay, in the clouds, in the convective cloud. Actually, that is true for the convective clouds. When we talk about the diagram or skew log diagram, that is valid only for the convective cloud. That means cumulus cloud, cumulonimbus cloud, etc. Okay, that's not valid for the stratiform cloud. Right? That you should know. I hope you know by now. The diagram, when we talk about the diagram, that actually refers, that is actually utilized for the convective clouds, not for the stratiform clouds. Okay, so in this diagram that you see, is the diagram? Yeah, okay. This is okay. We have talked about this is last time. What you see in this diagram is, say, liquid water content in grams per cubic meter in the y-axis, okay, versus the distance, okay, versus the distance in kilometer. And as you can see, the cloud liquid water content fluctuates or varies with the distance. All right. And this line, the dashed line that you see, this dashed line clearly visible to you. This dashed line clearly visible to all of you or not?
Yes, sir.
Yeah, okay, great. So this dashed line shows the adiabatic liquid water content estimated from the diagram. Okay, and this is what is computed, or you can say measured rather, more appropriately. These are the measured cloud liquid water content inside the cloud. Okay, the one observed by measurements using different instruments. Okay, either through flying the aircraft or by any other means. Okay, flying balloons, etc. So what you can see is that the measured amount of liquid water content is much below the estimated value from the adiabatic liquid water content obtained from the Scuti log P diagram or diagram. All right, and that happens because in the diagram generally we do not consider the effects of the entrainment. You know entrainment, right? We have discussed about the entrainment in the previous classes a lot, right? So because of the entrainment, or the entrainment is not really considered in the diagram or Scuti log P diagram, and therefore the adiabatic liquid water content which is obtained from the diagram is much higher than compared to the one which is actually measured by instruments inside the clouds. Okay, and this happens because due to the entrainment is basically, as you know, is some sort of a turbulent process, right? Turbulent process because the lateral boundary of the clouds, okay, the lateral walls of the clouds are continuously eroded, because of the turbulent mixing between the surrounding air and the cloud air. Okay, so because of that, the cloud liquid water gets evaporated, gets continuously evaporated, and therefore the amount of cloud liquid water which we measure, or which are measured, is less than what is estimated or what is shown by the adiabatic lapse rate, adiabatic liquid water content. Okay. Now in this diagram also the same thing is represented in a different way. For example, on the x-axis, what you see is the liquid water content in grams per cubic meter, and in the y-axis you see the height above the cloud base. Okay, because all these liquid water contents are inside the cloud, which is above the base of the cloud, right? And as you can see, all the measurements are less than the adiabatic liquid water content, which is shown by the red line here. And this happens because of the, as I said, entrainment which continuously occurs. Okay, here the blue dots, these are the average liquid water contents measured in 802 cumulus clouds. Okay, all these blue dots are the measured amount of liquid water content in about 800 cumulus clouds. Okay, and these squares are representing the largest measured value. These squares are representing the largest measured value of the liquid water content. Even that also is less than the adiabatic liquid water content, which is shown here by the red line, right? Same diagram as we have discussed, and this is what is shown here schematically about the entrainment. Okay, this is the cloud parcel. As you can see, bubble, cloud bubble is rising. Okay, they are the cloud-based mass flux which are upward, showing upward direction. The cloud air mass is rising up. Okay, and along the lateral boundary as well as from the top of the cloud. Okay, entrainments are taking place. Also, when the cloud becomes matured, like a full-fledged cumulonimbus cloud, then retrainment starts from the top of the cloud. There are lateral retrainments also, of course, but then the cloud top retrainment is much larger in magnitude than compared to the lateral retrainment from the cloud. Okay, so entrainment and retrainment, two opposite processes, right? And so here, this is the rising thermal, right? This is rising thermal, and these are all the cloud air. Okay, so the rising thermal and the cloud air are continuously eroded by the entrainment, and because of that, as you can see from this diagram, the cloud liquid water as measured by instruments are less in magnitude than compared to the adiabatic liquid water content. Okay, because some of it gets evaporated, right? So measurements in and around the small cumulus clouds suggest that entrainment occurs primarily at the tops as symmetrically shown in the diagram. Well, this is the case for the growing phase of the cumulus cloud, as you might have read or studied, or may study later also, that the cumulus cloud or the convective clouds go through three life cycle, or there are three phases in their life cycle. One is the growing stage, other is the matured stage, and third is the dissipating stage or dissipating phase. Okay, so this illustration, this diagram which you are seeing, is actually for the growing phase of the cumulus cloud, in which there are entrainment taking place also from the top of the cloud. But when the cloud is matured, like a full-blown cumulonimbus cloud, you have got the entrainment from the top of the cloud. Okay, as entrained air is entrained at the top of the cloud, is distributed to lower levels. Okay, once it is entrained, the surrounding air is mixed with the cloud air, and then it comes down, is brought down. Okay, lower levels. When cloud water is evaporated to saturate an entrained parcel of air, the parcel is cooled. Okay, the parcel is cooled because of the evaporation, right? Because of the evaporation. If sufficient evaporation occurs before the parcel loses its identity by mixing, the parcel will sink. Okay, mixing with more cloudy air as it does so, right? And in a blown up, fully matured cumulonimbus cloud, as you know, somewhere below the top of the cloud, the downdrafts originate. Okay, one of the major cause for the downdraft is the evaporation, cooling because of the evaporation, okay, of the cloud droplets, and second is because of the raindrops, weight of the raindrops, which are pulled down because of the gravity. So the downdrafts originate somewhere below the top of the cloud, and then they spread out from the base. Okay, they spread out from the base, and what we find when we are standing, close to a approaching cumulonimbus cloud, then we start feeling chilled air because of the downdrafts which are originating somewhere at a high altitude from the top of the cloud, okay, and then spreading down outside the base of the cloud. Okay, The shrinking parcel will descend until it runs out of negative buoyancy or loses its identity. Such parcel can descend several kilometers in a cloud, even in the presence of substantial updraft, in which case they are referred to as penetrative downdrafts. Penetrative downdraft. Okay. I mean the the evaporated no, the cooling because of the evaporation is so strong, which makes the cloud air heavy, and also the weights of the raindrops, which are continuously forming and growing inside, are so strong that the updrafts are unable to sustain them inside the cloud. Strong updraft also, and also I probably we have discussed earlier that the strength of the updraft, the speed of the updraft is quite strong, much stronger than the downdraft inside the cloud. Okay, but even then, it is unable to sustain the penetrative, the sinking cloud air mass. Okay, and so the downdraft that occurs is called the penetrative downdrafts. Normally, in a very strong, cumulonimbus cloud, sometimes let me give the drawing board. Sometimes if you have a strong, mature cumulonimbus cloud, then updrafts are there. Okay, the updraft speed can be sometimes very high. I mean, it approximately say 10 to 20 meter per second also. Updraft speed. Okay, the downdrafts are much weaker. Much weaker, and its speed is, approximately say, depending upon how much mature the cloud, about 4 to 5, let us say, meter per second. Okay, but even then, such a strong updraft is unable to sustain the cloud hydrometeors. Okay, and the weight of the cold cloud air mass, and so it penetrates down, and so we call it penetrative downdrafts. Okay, penetrative downdrafts. Right. Over large areas of the oceans, stratocumulus clouds often form just below a strong temperature inversion at a height 0.5 to 1.5 kilometer. Okay, which marks the top of the marine boundary layer. You might have heard about the trade wind cumulus, trade wind zone. You have heard about the trade winds, right? In your school geography classes, you might have studied about the trade winds. Have you heard about the trade winds or not? Have you studied about the trade winds in your school? Yes or no?
Yes,
Am I
sir.
audible? Yeah. So,
Yes, sir.
yeah, in the trade wind, which are generally in the subtropics, right? Tropics and subtropics, right? Trade winds are generally in the subtropics about the large part of the ocean. That part of the earth is actually covered by ocean, right? And in the trade wind zone, people who have traveled by ships and also who fly, they know, they have seen that for hundreds of kilometers, there are stratocumulus clouds, trade wind cumuli. We call it trade wind cumuli. Okay, and generally their base is about zero point 0.5 to 1.5 kilometer above the ground. Okay, and which is approximately also the top of the marine boundary layer. Top of the marine boundary layer. Okay, that typical height of the boundary layer is about 1 kilometer. Right. So the tops of the stratocumulus clouds are cooled by long wave radiation to space. Okay, right? Like we have got a stratocumulus cloud. You've got several stratocumulus cloud all in the matured stage. Okay, different size and different shapes. Okay, so the tops of the cumulus clouds are cooled because of the long wave radiation. Okay, long wave radiation. This is cool because of the long wave radiation. Okay, and the bottom part is warm. The lower part is warm. Okay, because of the uh, radiation which is going upwards. Okay, from the Earth's surface, right? So because of the cooling at the top and warming at the base, the clouds get destabilized. Cloud plates will destabilize. Okay. So the differential heating drives shallow convection in which cold cloud air sinks and droplets within it tend to evaporate, while the warm cloud air rises. Okay, and the droplets within it tend to grow. Okay, so there are continuously rising bubble, okay, rising thermals from this Earth surface because Earth surface is heated hotter than the air above. So the thermals rise above, okay, warm thermals rise above, and the and the and the upper part of the clouds, which is cooled by the radiation, they shrink, okay, and so the cloud gets destabilized. These motions are responsible in part for the cellular appearance of a stratocumulus. If you look at the satellite images, sometimes now you can see for a long distance for hundreds of kilometers, the stratocumulus clouds are present and they look like cellular structure. Okay, something like this. You must have seen. Have you seen these kind of images uh, taken even by the aircraft? We fly by the aircraft, or the ocean. You can find for long distances. This kind of clouds are there. Okay, they are all stratocumulus cloud. Okay, this image, this photo is taken from above, maybe by flying aircraft. Okay, and as it shows that actually there are patterns. If you look at closely, there are patterns in these clouds. Okay, the long streets. Okay, empty region, cloudy region, empty region, cloudy region. You can see long streets of the stratocumulus cloud. They are aligned for hundreds of kilometer distance, and that also depends upon the wind flow pattern. Wind flow pattern, and also if you see it minutely, you can see some kind of a cellular structure here, and that's because the upper part is sinking, the lower part is rising because of the warming from the base and cooling at the top. Okay, so these motions are responsible in part for cellular appearance of stratocumulus clouds. Okay, the entrainment of warm, dry air from the free troposphere into the cool, moist boundary layer below plays an important role in the marine stratocumulus top boundary layer. Okay, the rate at which this entrainment occurs increases with the bigger of the boundary layer turbulence, but it is hindered by the stability associated with the temperature inversion. Okay, there are so many things concurrently existing in the atmosphere. Okay, turbulence is taking place on one side. Okay, there is a vigorous turbulence rather. Okay, and there is also the temperature inversion. Okay, so the temperature inversion acts like a barrier. Okay, it doesn't want to, it doesn't allow the cloud air to penetrate through it because it causes stability to increase. Now, as you might have seen, when there is an inversion, then the atmosphere is stable. Okay, the parcels cannot rise. Okay, if there is an inversions, we have got a temperature inversion. Suppose this is a T and this is Z. Okay, and this is, instead of decreasing somewhere it is increases and again decreases. So this is the inversion layer. Okay, and this inversion layer, okay, this inversion acts like a stable boundary. Okay, or it acts like a now wall which does not allow the clouds to penetrate go up because atmosphere is stable. Okay, so similarly also the air, cloud air above this, which are sinking down, okay, sinking down, it is prevented by this inversion layer. Okay, so It depends upon the vigor of the boundary layer turbulence, but it is also hindered by the stability associated with the temperature inversion. So now let's talk about the growth of the cloud droplets in the warm cloud. We are talking about the warm clouds only so far, okay, and how the droplets grow in the warm clouds. We had talked a little bit earlier about initially how uh, the embryonic cloud droplets grow because of the condensation, right? And then further, they will grow depending upon many factors. Like one of the important factor is how are they able to collide with the droplets surrounding it. Okay, so we shall talk more in detail about that now. In warm clouds, the droplets can grow by condensation initially in a supersaturated environment and by colliding and coalescing with other cloud droplets. Okay, a very important droplet growth by collision and coalescence process is one of the important process for the cloud droplet growth in the warm cloud. Okay, now let's talk about a little bit in detail on the growth of droplets by condensation. Now let's consider first an isolated droplet, okay, with radius r at a time t, situated in a supersaturated environment in which the water vapor density at a large distance from the droplet is rho v infinity. Okay, this is the water vapor density. Okay, wherever we see v, okay, v subscript v indicates the vapor phase. Okay, so this is the density of the water vapor at a large distance, let us say represented by infinity, and the water vapor density adjacent to the droplet is rv rho v r. Okay, when r is the radius. Okay, at a time t. If we assume that the system is in equilibrium, that is, there is no accumulation of water vapor in the air surrounding the drop, the rate of increase in the mass m of the droplet at a time t equal to the flux of water vapor across any spherical surface of radius x centered on the droplet. We are basically trying to develop equation or compute the rate of change of mass of the cloud droplets with time, okay, or the rate of change of the droplet size or radius of the droplet with time. Okay, that's what we're trying to compute or develop equations for that. Sorry. Hence, if we define the diffusion coefficient d of a water vapor in air as the rate of mass flow of water vapor across the normal to it to a unit area in the presence of unit gradient in the water vapor density, the rate of increase in the mass of water droplet is given by dm by dt equal to 4 pi x square d times d rho v by dx. Okay, m is the mass of the water droplets. Okay, d is the diffusion coefficient. Okay, 4 pi r square, as you know, is the area. Okay, cross sectional area, 4 pi r square. Okay, of the spherical droplets. X is the distance. Okay, and also the rate of change of water vapor density with distance. So this is what determines the change in mass of the water droplet with time. Okay, rho v is the water vapor density at distance x is a function of the r droplet radius from the droplet, because under the steady state condition dm by dt is independent of x. The aforementioned equation can be integrated as follows. We are assuming steady state, in which case dm by dt is in equilibrium. Okay, so we can write dm by dt integration from x equal to r, the radius of the droplet, to a large distance x equal to infinity, dx by x square is equal to 4 pi d, where d is the diffusion coefficient, integration of the d rho v from rho v at r to rho v at infinity. Okay, the density of the water vapor at the distance of the radius of the cloud, and or you can say at the surface of the cloud droplets and at a large distance. Okay, so this is what will determine the rate of change of mass of the cloud droplets. Or we can write from this equation dm by dt is equal to 4 pi rd times rho v at infinity minus rho v at r. Okay, trying to simplify it. Okay, assuming the equilibrium condition, we're trying to simplify this equation to determine the rate of change of mass of the cloud droplets. Okay, so let's say this is equation number 7. Now substituting the mass of the spherical water droplets by this expression 4 by 3 pi r cube. You know, this is the volume, right? You know that volume of the sphere 4 by 3 pi r cube, r is the radius, and times rho L, where rho L is the density of the liquid water. Okay, rho L indicates the density of the liquid water. Okay, so this is the mass of the spherical cloud droplets having liquid water inside it. Okay, we substitute this value of m into this last expression. Okay, we can write dr by dt, where r is the radius of the cloud droplets, the rate of change of radius of cloud droplet is equal to d divided by rho times r times rho l times this rv at infinity minus rv at r. Okay, and finally, using the ideal gas equation for the water vapor and with some algebraic manipulation, we can get dr by dt. Okay, the rate of change of cloud water droplet radius with time is equal to 1 by r d times rho v at infinity divided by rho l e times infinity. Okay, where is the vapor pressure at the large distance infinity, e infinity minus er. Okay, so this is the expression which gives us the rate of change of water droplet radius with time. Okay, this is equation number 8, where this E infinity is the water vapor pressure in the ambient air well removed or well away from the droplet, and ER is the vapor pressure adjacent to the droplet, almost you can say at the surface of the water droplets. For droplets in excess of 1 micron meter or so in radius, it can be shown that the vapor pressure ER is approximately equal to the saturation vapor pressure ES. Okay, ES is the saturation vapor pressure over a plane surface of pure water. Okay, which depends only on the temperature. So in this case, if E infinity is not too different from ES, okay, we can write E infinity minus ER divided by E infinity is approximately equal to E infinity minus ES divided by ES. Okay, where this is replaced by the saturation vapor pressure. Okay, saturation vapor pressure, and this let us denote it by S. Okay, let's denote this by S. So, where S is the super saturation of the ambient air. S is the super saturation, E infinity minus S divided by S. S is the saturation vapor pressure, and this is the vapor pressure at a large distance infinity. So this is the saturation or super saturation vapor pressure of the ambient air. Okay, so this equation 8 then becomes r dr by dt equal to gl times s. And further simplify it, this equation, the rate of change of radius of the water droplets with time is equal to gls, where gl is equal to d times rho v from this equation. Okay, from this equation, g times d times rho v at infinity divided by rho l. So using this expression, now we can write this equation, okay, in a very simple form, r dr by dt equal to gls, where gl is the d rho v at infinity divided by rho l, where rho l is the density of the liquid water. Okay, density of the liquid water. Rho v is the density of the water vapor at a distance large distance infinity. D is the diffusion coefficient. Okay, so now see the simple. We have got the simplest relationship or simplest expression for computing the rate of change of growth of the water droplet radius with time, okay, which has a constant value for a given environment. It can be seen from this equation 9, this equation 9, that for fixed value of Z, and the supersaturation S dr by dt is inversely proportional to the radius of the droplets. So dr by dt is inversely proportional to the radius of the droplets. That means larger the droplet radius, smaller the dr by dt. Smaller the radius droplet, larger with the dr by dt. That means that smaller droplets are quickly rising in size, okay, rising in size because of the supersaturation which are existing around it, okay. So consequently, the droplets growing by condensation initially increases in radius very rapidly, but the rate of growth diminishes with time, as shown schematically by a curve in this diagram, okay. In this diagram, what you are showing is that the growth of the droplet radius with time, okay, growth of the droplet radius with time. And this blue curve is showing you the growth without any collision. It's just showing you the growth because of the condensation and coalescence. So as you can see that initially the droplet is quickly growing inside, very rapidly growing inside, but slowly after some time, the rate of growth slows down. The rate of growth of the water droplets slows down. Okay. The red curve actually indicates the red curves actually indicates the growth because of the both collision of the raindrops. I mean cloud droplets within the cloud. Okay. So that means no, and this is much rapid. As you can see that the red curve shows that the growth is much faster, much rapid than compared to the blue curve. Okay. The blue curve is the growth only because of the condensation and coalescence, and the red curve is because of the growth due to the collision of the water droplets, okay, cloud liquid water droplets. So the growth of the water droplets inside the clouds, in the real clouds rather, cannot be explained alone by the condensation and coalescence process. Unless there is a collision also, the water droplets cannot grow too much large, which we see in reality in nature many times. Okay. So this figure is schematic, shows a schematic curves of the droplet growth by condensation. This is the curve number A from the water vapor phase, and by collection of droplets. This is the red curve. Collection means that means this is just colliding and then becoming one. The two droplets become one droplet, bigger droplet. In a cloud, we are concerned with the growth of a large number of droplets in a rising air parcel. As the parcel rises, it expands, cools adiabatically, and eventually reaches saturation with respect to the liquid water. Okay. So further uplift produces supersaturations that initially increases at a rate of proportional to the draft velocity. As the supersaturation rises, the cloud condensation nuclei are activated, starting with the most efficient one. Okay, activated. We had discussed about what is meant by activated. Okay, what is active growth and what is inactive. Okay, inactive growth. When the rate at which water vapor in excess of supersaturation made available by the adiabatic cooling is equal to the rate at which water vapor condenses onto the cloud condensation nuclei and droplets, the supersaturation in the cloud reaches a maximum value. Okay, reaches a maximum value. The concentration of cloud droplets is determined at this stage, which generally occurs within 100 meter or so of the cloud base, about 100 meters above the cloud base, is equal to the concentration of the cloud condensation nuclei activated by the peak supersaturation that has been attained. Okay. Further, Consequently, the growing droplets consume water vapor faster than it is made available by the cooling of the air, so the supersaturation begins to decrease. And once the supersaturation decreases, the growth halts. The haze droplets, in this case, now the haze droplets will form and they begin to evaporate while the activated droplets continue to grow by condensation. Because the rate of growth of droplet by condensation is inversely proportional to its radius. The smaller activated droplets grow faster than the larger droplets. Okay, because they keep growing. The smaller activated droplets they keep growing and say they grow faster. Okay, than the larger droplets. Okay, consequently, in this simplified model, the size of the droplets in the cloud become increasingly uniform with time. Okay, that is, the droplets approach a monodispersed distribution. Monodispersed distribution. Okay. The sequence of events is illustrated by the results of theoretical calculations shown in this figure. Okay, 12. The sequence of events uh, is shown in this figure by theoretical calculation. And what it shows here is the droplet radius, the growth of the droplet radius versus time. Okay, time is in the x-axis. On the y-axis, one side is the droplet radius and the other side is the supersaturation. Okay, and you can see the various curves. Okay, various curves representing different ratio Im by ms to the power minus 15, minus 16, minus 17. This is the line of supersaturation. Okay, line of supersaturation, red curve. This is Im by ms to the power minus 18, to the power minus 19, and so on. Okay, so what it shows is the theoretical computations of the growth of the cloud condensation nuclei by condensation in a parcel of air rising with a speed of 60 centimeter per second. Okay, the parcel is rising at a speed of 60 centimeter per second. All right. Note how the droplets that have been activated. Now these are droplets have been activated like this red, or I can say brown curve, this blue curve. Okay, these curves, even this one. Okay, they are the activated. Purple curve, purple, blue, and brown curves are the curves which represent activated droplets. And see how they are rising, quickly increasing with time. Okay, the droplet radius is increasing rapidly with time. Okay, and these are like more like a non-active or non-activated droplets. Okay, so you can see that how the droplets that have been activated, there is a brown curve, blue curve, and the purple curve. Okay, approach a monodispersed size distribution after just 100 seconds. Okay, this is 10 seconds, this is 100 seconds. Just after the 100 seconds, how fast they have grown up. Okay, the variation with time of the supersaturation of the air parcel is also shown by the dashed red line, that means this one. Okay, this line, this dashed line shows the variation with time of the supersaturation of the air parcel. Okay, all right. So the comparisons of the cloud droplet sizes distributions measured a few hundred meters above the basis of the non-precipitating warm cumulus cloud with droplets size distribution computed assuming growth by condensation for about 5 minutes. Okay, show good agreement in this figure. Okay, this figure shows the droplet concentration versus droplet radius. Okay, droplet concentration versus droplet radius computed versus the measured. Okay, computed versus the measured. And this is, you can see that they are in good agreement. Okay, the two curves are in good agreement. The measured cloud droplet radius versus concentration and the computed theoretically computed using the model. Okay, this figure shows comparison of cloud droplet size distribution measured 244 meter, okay, 244 meter above the base of warm cumulus cloud, okay, 244 meter above the base of the warm cumulus cloud, and the corresponding computed droplet size distribution, assuming growth by condensation only, okay. This blue is the growth by condensation only, this one, okay, and this is the computed value. Note that the droplets produced by condensation during this time period extend up to only about 10 micron size. Okay, 10 micron size. Okay, so the blue line, which represents the computed value, blue line represents the computed value. Red line represents the value obtained or produced by condensation. Okay, during that time. So the droplets produced by condensation during this time period extend up to about 10 micron in radius, approximately 10 micron in radius. Okay. Moreover, as mentioned earlier, the rate of increase in the radius of droplet growing by condensation decreases with time. Okay. It decreases with time as we had seen in the previous diagram, figure number 12. Okay. So it is clear, therefore, as first noted by Reynolds in 1877, that the growth by condensation alone in warm cloud is much too slow to produce raindrops with radii of several millimeters. Okay, if the cloud droplets grew only because of the condensation, then their growth would have been so slow that they wouldn't have represented, or they wouldn't have been as seen in reality. Okay, as seen in reality. In which case, raindrops sizes can be a few millimeters, whereas the size of the cloud droplets are only in terms of the micron, right? Yet rain does form in the warm clouds, right? You know that if condensation was the only process, then the cloud droplets whose sizes are in terms of the micron, okay, micron size, would not have become large enough as seen by the radius of the raindrops, which are several millimeters in sizes. Okay, therefore, the condensation alone is not sufficient for the growth of the cloud droplets, and rain does occur. Okay, and so therefore there is another process which activates it further, much more vigorously or rapidly. Okay, the enormous increase in size required to transform cloud droplets into droplets, raindrops, is illustrated by the scale diagram in this figure. Okay, now this diagram is illustrating various things. Okay, the cloud condensation nuclei, let's say this black dot represents the cloud condensation nuclei whose radius is about 0.1 micron. Okay, 0.1 micron. And the number concentration of such CCM is about 2 or 6, okay, per cubic, okay, per cubic centimeter. And this V is the terminal velocity, okay, terminal velocity 0.0001 is the terminal velocity, okay. Now from this CCM, after the growth of the water droplets, you see the typical size of the cloud droplet, which is approximately this one, scaled to this one compared to this CCM size. Now the cloud droplets have become larger, and the radius is now 10. From 0.1, it has increased to 10, and the number concentration, of course, is the same. Okay, and also the V, the terminal velocity, has increased because as the size increases, as the size of the cloud droplets increases, the terminal velocity will also increase. Okay. Now, from this typical cloud droplets, which are still very small, okay, having micron, 10 micron radius, okay. Now it has further increased into large cloud droplet, okay, by the collision or collection of the water droplets as it falls in its way, okay, falls down in its way. So this is a larger cloud droplet. This is a typical cloud droplets, much smaller in size, about 10 micrometer, and this is large cloud droplets having radius equal to 50 micron, okay, 50 micron size, and the number concentration of such large droplets has decreased also, because larger the size, lesser will be their number, okay. So from 10 power 6 in number, it has decreased now down to 10 power 3. And also because the size of the droplet has increased, so the gravity will have more influence on this larger size, and so the terminal velocity also has increased, okay, from 1 to 27, okay, 1 to 27. Further it grows into raindrops, okay, and this spherical drops represents a typical formation of the raindrops, okay, conventional borderline between the cloud droplets and the rain droplets. Okay. Now here the radius has further increased to 100 micrometer. Okay, from 50 micrometer. Right. So from zero point 0.1 to 10 to 50 to 100 micrometer, it has increased in size, and also its terminal velocity, fall velocity, has also further increased. Okay, from 1 to 27 to 70. Okay. Now this is the borderline, okay, borderline of the formation of the raindrops, okay, formation of the raindrops from the cloud water droplets, okay. These are the cloud water droplets, smaller droplets, larger droplets, and this is the formation of the raindrops, okay. And further it can grow, and its size can become about 1000, okay, micrometer, about a few millimeter in size, that means. And obviously then the number concentration will also reduce, so it has reduced to 1, okay. Here it was at about 3, and it has reduced down to 1. And then V, the terminal velocity, has further increased because size has become larger, and so its mass also has become larger, and therefore the terminal velocity has increased to 650. Okay, so the enormous increase in size required to transform cloud droplets, okay, into raindrops is illustrated in this scaled diagram. Right? Now this figure shows the relative size of the cloud droplets and the raindrops. Okay, here R is the radius in micrometer, N is the number of particles per liter of air, and V is the terminal velocity, fall velocity in centimeter per second. Okay, in centimeter per second. The circumferences of these circumferences are drawn approximately to a scale, but the black dot, this one, representing a typical Sicilian, is 25 times larger than it should be relative to the other circles. Okay, this is the Sicilian black dot. For a cloud droplet 10 micron in radius to grow to a raindrop of 1 millimeter, typically the radius of the raindrops are about 1 millimeter. So for a cloud droplets of 10 micron in radius to grow to a raindrop of 1 millimeter size requires an increase in volume of 1 million fold. Okay, it requires an increase in volume of the 1 million fold. So much of increase is required. So much of increment is required. Okay, and that's what we also see normally in the nature. Okay, however, only about 1 droplets in a million, about 1 per liter in a cloud, has to grow by this amount for cloud to rain. Okay, only 1 per liter. Further, because from the cloud droplet, it has converted into raindrop, and for this only 1 droplet per liter, that is 1 in a million in the cloud air, has to grow by this amount for the cloud to rain. The mechanism responsible for selective growth of a few droplets, okay, into the raindrops in warm clouds is discussed in the next section that we shall discuss further. Okay. So, is that okay? Shall we continue for today or shall we stop for today? What do you think? Am I audible? How many of you are there? 8 of you are there. 8 of you are there. So, am I audible and visible to all of you?
Yes, sir.
Yes.
Okay. Yeah. Bobin and Deepak, I see some of you have joined later on. Still Lakshmi also has joined later on. So, okay. So, Kusum also has joined later on. Okay. So, do you think that we shall stop for today? Becoming too much for one class, or shall we continue? Because we have to discuss many more things. Like after this, we shall discuss about the terminal velocity of the raindrops. Okay, terminal velocity of the raindrops. Then we shall discuss about. I too joined late. Who is that? Mobin. Okay, Mobin joined late. Yes. Yeah. So then after discussing the warm cloud growth, then we shall discuss about the growth of the cold clouds. Okay, just discussing so far the growth of the water droplets in the warm cloud, and after that we shall discuss about the growth of the water droplets in cold clouds. Okay, and after that our this part of the chapter will be complete. Okay, another I think 3-4 classes or two minimum 3-4 classes approximately it may take to complete the cloud microphysical processes. We are talking about the cloud microphysical processes, growth of the cloud droplets into raindrops of the warm cloud and the cold cloud. Okay, we shall start cold cloud maybe in the next class. Okay, and after that we shall discuss about the electrification of the clouds. Okay, or atmospheric electricity. So hopefully, I think about 3 to 4 classes for the cloud microphysical parameters and another 3 to 4 classes for the atmospheric electricity. About 8-9 classes, or let us say maximum 10 classes, our syllabus will be over. Okay, and today is 27th of March or February. Tomorrow I'm traveling. Tomorrow Sunday also. Tomorrow cannot have class. So Monday is 1st March. So from Monday, if we have 4 hours in a week, okay, 4 classes in a week. So uh, from coming Monday to the next Monday will be 7th of March. We'll have at least 8 classes. If we have just no, we have 4 classes only. From coming Monday to the next Monday, we'll have only 4 classes, and then after that, the next week we can have another 4 classes. So how much? What 1st March to 15th of March? We can have only 8 classes. So I think now we have to go
Sir,
faster. Ah, yeah,
sir,
Deepak.
from March 8 our exams are starting.
Yeah, what I was discussing in the beginning before you came today. So March 8, your classes, our exams are starting. So preferably we should try to finish your syllabus before that, and also complete your internal assessment before that. Okay, second internal assessment. I was discussing this before you came today. So if so, then we have got only 8 days left. So tomorrow Sunday I cannot take class. I'm traveling. Okay, and first is Monday. So from Monday to the next Monday, your Monday for your first paper. Have you got the timetable of exam, Deepak?
Sir, no, sir,
Deepak,
not yet.
no, not yet. Okay. I think your first examination, the first paper may be on 9th of March. Okay. Um, and this cloud physics, or sorry, this atmospheric physics will be probably at the end of your all papers. Okay. So, but nevertheless, because your exams will start, so I will definitely like to finish this syllabus before your exam starts. Okay. Unless, and I mean, if it is okay for you, then I can continue taking class slowly. Because now, so far, so I've been going very slow. But now I have to go faster. Because unless we go faster, your syllabus will not be completed. Right. And as I estimate that we need about 10 classes to complete the remaining syllabus, about 10 classes. All right. So, this coming week, we can have only 4 classes. 1 week, we have 4 classes. And then after that, the next Monday is 8th, then Tuesday is 9th. I think your exams will start from Tuesday. So, it seems that unless we have 2 classes per day, in the next 1 week, it will be difficult to complete the syllabus. Or otherwise, I have to rush. I can complete the syllabus in just 2-3 lectures also. But in that case, I will have to rush. And I want you to understand rather than just finish the syllabus. See? Understanding the subject is one thing, and finishing the syllabus is another thing. Right? And this is your actually foundation. So I want the foundation to be made stronger. Right? And that's why I've been going so slow. Otherwise, I think by now, if I count all the classes, although there were about 45 recorded lectures, but we might have had more classes than that, which are not recorded. Okay, we have 45 recorded lectures, but there are many unrecorded lectures. Initially, 4 or 5 lectures we did not even record. So altogether, we must have taken about 50 classes or more than that so far. Okay, but I mean that is just to complete the fulfill the requirement. Just to fulfill the requirement. But as I said, that it is more important to learn, okay, the subject, understand the subject, than just to finish the syllabus. Okay, and as I said, I can finish the syllabus in about 3 to 4 lectures, but that will be, I think, not fair because you will not learn much, uh, and somehow syllabus will be completed. So be prepared to have at least one or minimum 1 class per day, or you can have 2 classes also per day. Okay, and so we can have classes in the odd time also. In that case, not necessarily always, during the working hour. We may have to take the class in the odd time. So, are you all ready for that? Tell me, yes or no? Hmm? I placed before you everything. Okay, you have got uh, cold clouds, the growth of water droplets in the cold clouds to cover. I can finish that in one lecture, but I don't want to rush it. I want you to understand so that your base is stronger. And after that, we have to cover the atmospheric electricity, which also I think 4 to 5 classes. So I need about 10 lectures, and you have got 1 week time before you start the final semester exam. Okay. Would you like to continue the classes when your final semester examination is going on? Tell me, yes or no? You have got, I think, 1 or 2 days break between each examination. You have got 1 or 2 days break. Sometimes 1 day break, sometimes 2 days break. So if you agree to attend 1 hour class while your examination is going on, then we can comfortably take 1 class per day and finish the syllabus before this exam. If you are not ready for that, then we'll have to take 2 classes per day somehow in the coming week and rush you to complete the syllabus. Choice is yours. One by one, I will ask all of you and tell me what is your opinion. I start with Anjali. Anjali, can you hear me?
Yes, sir.
Yeah, what is your opinion?
I
Hmm?
think we
You
can
can
take
switch on.
class.
Okay. Yeah,
Sir?
switch on your video. When you are talking, you can switch on your video. You can switch on your video and tell me what is your opinion. Okay, yeah, tell me.
I think we can take two classes per.
Okay, two classes per day so that your syllabus can be covered in 1 week, right? So your opinion is that when the examinations are going on, it's better not to have the classes, right?
Yes, sir.
Even if you have got 1 or 2 days break between each paper, but you prefer that uh, all the syllabus should be covered before the exam starts. Is that so?
Yes, sir.
Okay, that is your opinion. Muru, anyway, Syam doesn't have to write examination. Barsa, what is your opinion? Barsa, can you hear me? Are you there, Barsa?
Yes, sir.
Yeah,
Yes,
what is
sir.
your what is your opinion?
Sir, I think that as Anjali said, we can have classes like in the week before, but in during the exams, it won't be that comfortable.
Okay, so you prefer that we should not have classes during the examination, and all the syllabus, whatever it may be, should be completed before the exam starts. So maybe in that case, we can take classes on Saturday, Sunday also. Will that be okay? Hmm? Coming Saturday, we have got only
Uh,
one Saturday. Today is anyway Saturday. Tomorrow I am traveling. I cannot take the class tomorrow. Okay, so you have got another Saturday and Sunday before
Sir,
your
you can take extended class in the in weekdays only.
weekdays. Extended class means up to what time? Can we take classes up to 6:30, 7 o'clock? Up to will
Sir,
that be okay?
we did class in the evening when there was some problem, and for 1 month we did class in the evening,
Up to
so
what time?
that won't be any problem.
To what time? What time in the evening?
Sir, actually, it was like agreed upon. I think 7:30, and sometimes it was 6:30, like that.
Okay, so up to 7:30, you already have had the classes earlier,
Sir,
right?
we've earlier had classes like when Chinmay sir and Jayanti ma'am shifted the classes in morning. We had Chinmay sir's class in evening.
Okay, okay.
So that won't be any problem. If you want to take class, you can take
Make
it in
okay.
evening
So
also.
fine. So up to 7:30, we can take the classes, no problem, right?
Yes,
Yeah.
sir.
Oh, fine. So we can do that way. We can have two classes per day, maybe one in the morning and one in the evening. That way also because 11:30 to 12:30 to 1:30 anyway timetable we have the class, right? 12:30 to 1:30. So then another class we can take in the evening, maybe after 4:30 or 5:30 as per your free time. If you are free at 4:30, we can take the class at 4:30, or if free at 5:30, we can take the class at 5:30, right? So that next week we can take at least two classes per day, 2 hours per day, and then complete the syllabus by the weekend. Okay, Saturday, Sunday, right? So will that be okay?
Yes, sir.
Okay, great. Deepak, what is your opinion, Deepak? Deepak, can you hear me?
Yes,
Yeah. Is that okay? What is your opinion?
yes, sir. I think we can have two classes per day, sir. That would be
Okay.
better
And
than
extended
having classes
classes
during exam.
in the evening also we can have the class, right? On
Yes, yes, sir. Yes, sir.
okay, good, very good. Then who is this Mobin? Mobin, what is your opinion, Mobin?
So I think what's the opinion? I'm with Varsha's opinion. We can
Huh?
take it.